By the end of this video, you'll have the 2026 battery roadmap that separates actual production timelines from lab hype, so you can finally explain to stakeholders why lithium isn't dying, but why sodium-ion and solid-state are capturing specific margin-rich segments that most analysts are still missing. You'll walk away with the technical vocabulary and supply chain intel that makes you the most informed voice in your next strategy meeting. Because here's what nobody's telling you. While the internet obsesses over mythical aluminum-ion breakthroughs, Tesla has quietly filed patents that reveal their actual 2026 play, and it has nothing to do with what you've been reading. The lithium paradox. Tesla stock moved 3.2% in November 2025 on battery news, but the technology everyone thinks they announced doesn't exist yet. Let's start with the problem that's costing companies billions in misallocated capital. In early 2025, lithium carbonate prices spiked to $38,000 per ton before crashing back to $11,000 by August. That's a 71% collapse in 8 months. If you're a CFO trying to lock in battery supply contracts, that volatility is a nightmare. You can't build a $50 billion gigafactory strategy on a commodity that behaves like a meme stock. So here's the natural question. Is Tesla abandoning lithium entirely? The short answer is no. The sophisticated answer is that Tesla is executing a 3-phase material diversification strategy that most analysts are completely misreading. Phase 1 is already complete. Tesla has moved nearly all of its standard range Model 3 and Model Y vehicles to lithium iron phosphate chemistry. That's LFP. No cobalt, no nickel, just iron and phosphate. This wasn't a performance upgrade, it was a geopolitical hedge. Why? Because 80% of the world's battery-grade nickel refining happens in China and Indonesia. Cobalt? 70% of global supply comes from the Democratic Republic of Congo, where child labor and warlord financing remain persistent issues. LFP uses iron, which is the 4th most abundant element in the Earth's crust. But here's what's fascinating. LFP batteries are actually heavier and lower in energy density than the nickel-based chemistries Tesla used to use. An LFP pack delivers about 160 to 180 watt-hours per kilogram compared to 250 watt-hours per kilogram for a high nickel NCA or NCM cell. So why would Tesla willingly accept a lower range battery? Because LFP has a 50% longer cycle life. Real-world data from Chinese taxi fleets running LFP Model 3s shows less than 5% degradation after 130,000 miles. Nickel-based packs? They're hitting 10% degradation at 100,000 miles. And here's the kicker. LFP batteries can be charged to 100% every single day without damage. Nickel-based packs? Tesla's own software recommends you stop at 80% to preserve longevity. So the usable range of an LFP pack charged to 100% is often identical to a nickel pack charged to 80%. Tesla didn't abandon performance, they redefined it. But LFP is just phase 1. Phase 2 is where things get interesting. The 4680 crisis nobody talks about. Tesla's revolutionary 4680 cell was supposed to be in 3 million cars by now. Instead, a $2.9 billion supply contract just collapsed by 99.9%. Here's what went wrong. Let's talk about the 4680 format, because this is where Tesla's lithium strategy hits a wall that most people don't understand. At Battery Day in 2020, Elon Musk stood on stage and promised the world a new cell format, 46mm in diameter, 80mm tall. The 4680 cell was supposed to deliver 5 times the energy and 6 times the power of the previous 2170 format. The magic was in the tabless design. In a traditional cylindrical battery, there's a small metal tab that connects the electrode to the terminal. That tab is a bottleneck. It restricts electron flow and generates heat. Tesla's solution was to eliminate the tab entirely and use a shingled electrode design where the entire edge of the cell acts as the terminal. This reduces internal resistance by a factor of 5. Lower resistance means faster charging, less heat, and longer life. On paper, it's brilliant. In practice, it's been a disaster.
Here's why. Tesla decided to manufacture the 4680 using a dry electrode process. Traditional battery production involves mixing active materials with a liquid solvent, coating that slurry onto metal foil, and then drying it in massive ovens that are 3 stories tall and consume enormous amounts of energy. The dry process eliminates the solvent. You take powdered cathode material, compress it directly onto aluminum foil, and you're done. No drying, no toxic NMP solvent, no giant ovens. The environmental and cost savings are massive. But there's a problem. When you compress dry powder, it doesn't stick together uniformly. The particles clump. You get uneven density across the electrode, and when you roll that into a cell and start charging it, those uneven spots create localized heat concentrations. That's a thermal runaway risk. Tesla's solution, revealed in a November 2025 patent, is a composite binder system. They're mixing polytetrafluoroethylene, that's PTFE, also known as Teflon, with polyvinyl diidine fluoride, or PVDF. When you put this mixture through high-shear jet milling, the PTFE fibrillates. It forms a microscopic spiderweb structure that holds the cathode particles together in a flexible, self-supporting film. This allows the material to pass through calendaring rollers in just 3 passes instead of 10. That triples manufacturing throughput. But here's the problem: it's still not working at scale. In late 2025, South Korean cathode supplier L&F Company reported that its contract to supply high-nickel cathode material for Tesla's 4680 cells had been slashed by over 99.9%. That's not a reduction, that's a cancellation. What does that tell you? It tells you that Tesla's internal 4680 production lines are not ramping. The dry electrode process is still in the debug phase, and the only vehicle currently using 4680 cells in volume is the Cybertruck, which sold fewer than 50,000 units in 2024. And here's something I'm curious about, because this affects every EV owner watching this. If you own an electric vehicle right now, type the word range in the comments. I want to see how many of you prioritize maximum range versus how many would trade 50 miles of range for a battery that lasts twice as long, because that's the exact trade-off Tesla is making with LFP, and I think the industry is betting on the wrong answer. So if the 4680 is stuck in production hell, what's Tesla's backup plan?
The sodium-ion silent revolution. While everyone obsessed over solid state, a $40 per kilowatt-hour chemistry just hit commercial production, and Tesla filed a patent for it in 2025. Let me tell you about the technology that's actually going into production in 2026, and it's not what you think. Sodium-ion batteries. Yes, sodium, the same element you shake onto your fries. Here's why this matters. Sodium is 1,000 times more abundant than lithium. It's distributed evenly across every continent. You can extract it from seawater or from soda ash, which is mined in Wyoming, Turkey, and China. There's no geopolitical choke point, and the cost structure is extraordinary. CATL, the world's largest battery manufacturer, announced in late 2025 that its second-generation sodium-ion cells have reached an energy density of 175 watt-hours per kilogram. That's equivalent to entry-level LFP. But the cost? Projected at $40 per kilowatt-hour by 2026. For context, lithium iron phosphate is currently around $98 per kilowatt-hour. High nickel chemistries are $112 to $120 per kilowatt-hour. Sodium ion is 60% cheaper. Now you might be thinking, if it's cheaper, it must be worse, right? Not necessarily. Sodium ion has 3 advantages that make it ideal for specific use cases. First, low temperature performance. Lithium-ion batteries lose 20 to 40% of their capacity at minus 20 degrees Celsius. Sodium-ion? They retain 90% capacity at minus 40 degrees Celsius. If you're deploying EVs in Canada, Norway, or northern China, that's a game changer. Second, charge speed. Sodium ions are larger than lithium ions, but the intercalation mechanism in hard carbon anodes allows for extremely fast ion insertion. CATL cells can charge to 80% in under 20 minutes, even in freezing temperatures. Third, safety. Sodium-ion cells can be discharged to 0 volts and stored indefinitely without damage. Lithium-ion cells? If you over-discharge them, you risk dendrite formation and permanent capacity loss. But here's the most important part. Tesla knows this. In 2025, Tesla filed a patent titled Alloying Anode Active Materials for Sodium-Ion Energy Storage Devices. The patent describes the use of lead, tin, and antimony alloys in the anode to dramatically increase the volumetric energy density of sodium-ion cells. Why does that matter? Because volumetric energy density is what determines how much space a battery pack takes up in a vehicle. Gravimetric density, watt-hours per kilogram, gets all the headlines. But if you're designing a compact car or a grid storage system, you care about watt-hours per liter. Tesla's patent suggests they're targeting sodium-ion for 2 applications: stationary energy storage like the Megapack, and compact urban vehicles like the rumored $25,000 Model 2. And here's the confirmation. In early 2026, CATL announced that its first sodium-ion batteries will debut in a GAC Aeon vehicle. GAC is a Chinese automaker, but CATL supplies Tesla's LFP cells in China. If CATL is productionalizing sodium ion for passenger vehicles, Tesla is watching very closely. Now, if you're finding value in this breakdown, if you're starting to see the difference between what gets reported in the headlines and what's actually happening in the supply chain, hit that subscribe button. Because over the next 6 months, I'm going to be tracking every patent filing, every supplier contract, and every production milestone that tells you where this industry is actually heading. Not where bloggers hope it's heading, where the engineers are taking it. But sodium isn't the end of the story, because while sodium solves the cost problem, it doesn't solve the performance ceiling. For that, you need a different chemistry entirely. Let's talk about solid state, because this is where the hype machine has been running at full speed for 5 years. Solid-state batteries replace the liquid electrolyte in a lithium-ion cell with a solid ceramic, glass, or polymer electrolyte. This allows you to use a lithium metal anode instead of graphite. Why does that matter? Because lithium metal has a theoretical specific capacity of 3,860 mAh per gram. Graphite, 372 mAh per gram. That's a 10 times improvement. In practice, solid-state batteries could deliver energy densities of 400 to 500 watt-hours per kilogram. That would give a Tesla Model 3 a range of over 600 miles on a single charge. And because the electrolyte is solid, it's non-flammable. No more thermal runaway, no more battery fires. So why don't we have solid-state batteries yet? 3 reasons. First, dendrite formation. When you charge a lithium metal anode, lithium atoms don't deposit evenly. They form needle-like structures called dendrites. Over time, these dendrites can pierce the solid electrolyte and cause an internal short circuit. Researchers have tried everything to stop this, applying pressure to the cell, using mixed ion conductors, coating the anode with protective layers. None of it works reliably at scale. Second, interface resistance. The boundary between the solid electrolyte and the electrode is not a perfect chemical bond. There's resistance at that interface, which limits how fast you can charge and discharge the cell. Third, manufacturing cost. Solid electrolytes are expensive to produce. Lithium lanthanum zirconium oxide, LLZO, is one of the most promising materials, but it requires sintering at over 1,000 degrees Celsius. You can't just coat that onto aluminum foil like you do with a liquid electrolyte. So where does solid state actually stand in 2026? The leader is QuantumScape, a company backed by Volkswagen and Bill Gates. In late 2025, QuantumScape shipped its first alpha samples to automotive customers. These are 24-layer cells using a proprietary ceramic separator. They've demonstrated over 1,000 charge cycles with less than 10% degradation. They can charge from 10% to 80% in 15 minutes, and the energy density is around 380 watt-hours per kilogram. That's real, that's not lab hype. But here's the catch. QuantumScape's first commercial product won't be for cars, it'll be for consumer electronics. In early 2026, they announced a partnership with a top-tier consumer electronics manufacturer. Industry speculation suggests it's either Dyson or Apple. Why consumer electronics first? Because the cells are still too expensive and too low volume for automotive. A smartphone battery is 15 watt-hours, an EV battery is 75,000 watt-hours. You can afford to charge $200 for a solid-state phone battery. You can't charge $1.5 million for a solid-state car battery. QuantumScape's roadmap projects automotive-scale production by 2028 to 2030, and even then, it will likely go into premium vehicles first. Think Porsche, Audi, maybe the Tesla Roadster. But mass market? Not until the 2030s. So if solid-state is still 5 to 10 years away, what's Tesla doing right now? The Jeff Dahn longevity breakthrough. A 78-year-old Canadian professor just solved the million-mile battery problem, and Tesla has him on an exclusive contract through 2026. This is where Tesla's real competitive advantage becomes visible. In 2016, Tesla signed an exclusive research agreement with Dr. Jeff Dahn, a professor at Dalhousie University in Halifax, Nova Scotia. Dahn is not a celebrity scientist. He doesn't do TED Talks, he doesn't tweet, but he is the godfather of modern lithium-ion research. In the 1990s, Dahn helped develop the lithium cobalt oxide cathode that's used in nearly every consumer electronics battery today. In the 2000s, he pioneered high-precision coulometry, a diagnostic technique that can measure battery degradation at the parts per million level. And in 2025, his lab published a paper that changes the entire conversation about battery longevity. The title of the paper is Lithium-Ion Batteries with Lifetimes Exceeding 50 Years. Let me repeat that, 50 years. Here's how they did it.
Traditional lithium-ion cathodes are made of polycrystalline particles. That means each particle is made up of thousands of tiny crystal grains. When you charge and discharge the battery, lithium ions move in and out of these particles, causing them to expand and contract. Over time, the boundaries between the grains crack, the particle fractures, active material becomes electrically isolated, and the battery degrades. Don's solution: single crystal cathodes. Instead of using polycrystalline nickel, manganese, cobalt particles, his team synthesized single crystal NMC532. Each particle is one continuous crystal lattice, no grain boundaries, no crack propagation. The result? Cells that can survive over 20,000 charge cycles while retaining 80% of their original capacity. In automotive terms, that's 8 million kilometers, or 5 million miles. For a robotaxi, that's transformational. Tesla's Cybercab, the autonomous vehicle they unveiled in late 2024, is designed to operate 24/7 in a ride-hailing network. If the battery only lasts 500,000 miles, you need to replace it 3 or 4 times over the vehicle's operational life. But if the battery lasts 5 million miles, you never replace it. The battery outlives the vehicle. And here's the kicker. After the vehicle is retired, you can pull the battery pack and use it for stationary grid storage for another 30 years. That's the circular economy that Tesla has been talking about since 2020. But Don didn't stop there. His latest research involves a 2-additive electrolyte system. Traditional electrolytes use a cocktail of 5 or 6 additives to improve stability, reduce gassing, and prevent electrode corrosion. Don's team found that you only need 2, a vinylene carbonate derivative and a sultone compound. This simplifies manufacturing, reduces cost, and improves thermal stability at high temperatures. The cells can operate continuously at 85 degrees Celsius without significant degradation. Why does that matter? Because autonomous vehicles don't have downtime. They can't sit in a garage overnight to cool down. If you're running a robotaxi in Phoenix, Arizona, where ambient temperatures hit 45 degrees Celsius, you need a battery that can handle sustained heat. Don cells can. And Tesla has exclusive access to this research through 2026. Here's a question for everyone watching. If you could choose between a car with 400 miles of range that needs a new battery in 8 years, or a car with 300 miles of range that lasts 30 years, which would you pick? Type 400 or 300 in the comments, because that's the exact decision automakers are facing right now, and I think the answer is going to surprise the industry. But here's the strategic insight. Don's work isn't about replacing lithium, it's about perfecting it. Because if you can make a lithium-ion battery last 50 years, you don't need to replace lithium at all, you just need to recycle it better. Which brings us to the most important piece of the puzzle, the Redwood recycling endgame. J.B. Straubel left Tesla in 2019. His new company is now the largest battery recycler in North America, and it's about to make virgin lithium mining obsolete. Let's talk about J.B. Straubel.
Straubel was Tesla's co-founder and chief technology officer from 2004 to 2019. He designed the battery pack for the original Roadster. He oversaw the development of the Model S, the Gigafactory, and the Powerwall. Then, in 2019, he left. Most people thought he was retiring. He wasn't. He was starting Redwood Materials. Redwood is a battery recycling company based in Carson City, Nevada, right next to Tesla's Gigafactory, and in 2025 it became the most important company in the battery supply chain that nobody's talking about. Here's why. Redwood can recover over 95% of the nickel, cobalt, and copper from a lithium-ion battery, and they can recover over 80% of the lithium. That's not theoretical, that's happening right now at commercial scale. In 2025, Redwood processed 20,000 tons of battery material. That's enough to supply 30,000 electric vehicles. By 2030, they project they'll be processing 500,000 tons per year. That's 750,000 vehicles. But here's the key insight. The atoms don't degrade. When you use a lithium-ion battery, the lithium atoms don't disappear. They don't decay. They're still lithium. Same with nickel, cobalt, and copper. The only thing that degrades is the structure of the electrode. The crystal lattice fractures, the electrolyte decomposes, the separator breaks down. But the atoms, they're infinitely recyclable. Straubel describes this as the periodic table as a roadmap. Once you've mined enough lithium to electrify the global vehicle fleet, you never need to mine it again. You just keep recycling it. And here's where it gets economically interesting. Redwood doesn't sell recycled lithium carbonate to battery manufacturers. They sell cathode active material. That means they're not just recovering raw lithium, they're synthesizing it back into nickel manganese cobalt or lithium iron phosphate cathode powder, ready to be coated onto foil and rolled into cells.
This vertically integrated approach allows Redwood to undercut virgin material suppliers by 20 to 30% on price, while delivering a product with a 70% lower carbon footprint. And guess who their first customer is? Panasonic, Tesla's primary battery supplier. In 2023, Redwood signed a deal to supply Panasonic's Kansas battery factory with cathode materials starting in 2025. That factory is building cells for Tesla's US-made vehicles. So here's the loop. Tesla builds cars with Panasonic batteries. Those cars drive for 500,000 miles. The batteries get pulled and sent to Redwood. Redwood recovers the cathode materials and sells them back to Panasonic. Panasonic builds new cells. Tesla builds new cars. It's a closed loop. And as the volume of end-of-life batteries starts to surge in the late 2020s, remember, the first wave of Tesla Model 3s from 2018 will hit retirement around 2028. The supply of recycled materials will eclipse the supply of mined materials. This is what Straubel means when he says that battery recycling will be bigger than mining. But there's a geopolitical dimension to this that's even more important, because right now, 80% of the world's lithium refining capacity is in China. If you're a US or European automaker, you're dependent on Chinese supply chains. But if Redwood can recycle cathode materials domestically, you break that dependency. You achieve mineral independence without mining a single ounce of new lithium. And that's the real strategic endgame of Tesla's battery roadmap. If this level of supply chain analysis is what you're looking for, if you want to understand not just what's happening, but why it matters strategically, make sure you're subscribed, because in 3 weeks, I'm releasing a breakdown of CATL's vertical integration strategy that's going to change how you think about who actually controls the battery industry. And it's not who you think.
Tesla just opened a lithium refinery in Texas, but the process they're using produces zero toxic waste. Here's how they did it. Now let's talk about the one piece of vertical integration that most people are missing: Tesla's lithium refinery in Corpus Christi, Texas. This facility officially began operations in early 2026. It's the first lithium refinery built in the United States in over a decade. But it's not just a refinery, it's a statement. Here's the context. Refining lithium is a bottleneck. There's plenty of lithium ore in the world. Australia mines over 50% of global spodumene, but turning that ore into battery-grade lithium hydroxide requires high-temperature kilns, acid roasting, and chemical purification. And 80% of that refining happens in China. Elon Musk has called this a license to print money, because even though lithium ore prices crashed in 2025, refining margins stayed high. So Tesla decided to do it themselves. But they didn't just copy the Chinese process, they reinvented it. Traditional lithium refining uses sulfuric acid to leach lithium from spodumene ore. This produces lithium sulfate, which is then converted to lithium hydroxide. But it also produces sodium sulfate as a waste byproduct. Sodium sulfate is toxic and difficult to dispose of. It either gets dumped in tailings ponds or shipped to hazardous waste facilities. Tesla's process is acid-free. Instead of sulfuric acid, they use an alkaline leach method. The lithium is extracted using sodium hydroxide, and the byproduct is anhydrite, a calcium aluminum silicate. Anhydrite is not toxic. In fact, it's useful. Tesla is selling the anhydrite to concrete manufacturers who use it as a supplementary cementitious material. It reduces the amount of Portland cement needed in concrete, which lowers the carbon footprint of construction. So Tesla's refining process produces zero hazardous waste. It's a closed-loop, revenue-generating byproduct stream. And the capacity is significant. The Corpus Christi refinery can produce enough lithium hydroxide to supply 500,000 vehicles per year. That's roughly 40,000 tons of lithium carbonate equivalent. But here's the strategic play. Tesla isn't refining lithium to sell it. They're refining it to insulate themselves from price volatility. In 2022, lithium carbonate hit $80,000 per ton. In 2025, it dropped to $11,000 per ton. If you're trying to build a $25,000 electric vehicle, that kind of price swing can destroy your profit margins. But if you own the refinery, you lock in your input costs at the mining level. You pay for spodumene ore, which is relatively stable, and you control the conversion to battery-grade hydroxide. This is the same vertical integration strategy that Tesla used with gigafactories. Don't wait for suppliers to scale, build it yourself. And the location matters. Corpus Christi is a deep water port with direct shipping routes to Australia and Chile, the two largest lithium-producing regions. It's also 200 miles from Tesla's Austin Gigafactory. So the supply chain is ore arrives by ship in Corpus Christi, gets refined into lithium hydroxide, trucks to Austin, gets mixed into cathode slurry, coated onto foil, and rolled into 4680 cells, all within a 200-mile radius. That's not just vertical integration, that's regional autarky. But refining lithium is dangerous work. Let's not romanticize it. Workers at the facility are exposed to high-temperature kilns, fine mineral dust, and corrosive chemicals like lithium hydroxide, which can cause respiratory irritation and chemical burns. Tesla has implemented safety protocols, including respirators, protective clothing, and air filtration systems, but the risk is real. This is the hidden cost of the energy transition. We talk about clean energy, but the industrial processes required to produce batteries are anything but clean. That said, Tesla's acid-free process is a significant improvement over traditional methods, and as the refinery scales, it will be a critical piece of the puzzle for achieving domestic battery production.
Tesla isn't building one battery for everything. They're building 5 chemistries for 5 markets. Here's the segmentation map that Wall Street is missing. So let's synthesize everything we've covered and build the actual 2026 roadmap. Because here's the mistake most analysts make. They assume Tesla is searching for the one battery to rule them all. They're not. Tesla is building a portfolio of chemistries, each optimized for a specific market segment. Let me break it down. Segment 1. Premium performance vehicles. This is the Model S Plaid, the Model X Plaid, and the upcoming second-generation Roadster. These vehicles use high-nickel NCA chemistry in the 18650 or 2170 format. Energy density is 250 to 300 watt-hours per kilogram. The focus is on power delivery and range. These batteries are supplied by Panasonic and use cathode materials from Redwood's recycling stream. They're expensive, but the target customer doesn't care. They're paying $120,000 for a car. An extra $10,000 for the battery is irrelevant. Segment 2, mass market long-range vehicles. This is the long-range Model 3 and Model Y. These use either 2170 NCA cells or 4680 nickel-based cells, depending on production availability. The energy density is slightly lower than the premium segment, around 230 to 250 watt-hours per kilogram, but the cost is lower. As the 4680 dry electrode process matures, this segment will transition entirely to 4680 format with LFP or mid-nickel cathodes. Segment 3, mass market standard range vehicles. This is the standard range Model 3 and Model Y, as well as the rumored Model 2. These use LFP chemistry in the 2170 or 4680 format. Energy density is 160 to 180 watt-hours per kilogram. Cost is around $98 per kilowatt-hour. The focus here is cycle life and safety. These vehicles are targeting fleet customers, ride-hailing, and budget-conscious consumers who prioritize reliability over maximum range. Segment 4, autonomous robo-taxis. This is the Cybercab. These vehicles use Jeff Dahn's single-crystal NMC 532 cells in a custom 4680 format. Energy density is moderate, around 200 watt-hours per kilogram, but cycle life is extreme, over 20,000 cycles. The business model for robotaxis is miles per dollar, not miles per charge. A battery that lasts 5 million miles is worth far more than a battery that delivers 400 miles of range but only lasts 300,000 miles. Segment 5, stationary energy storage. This is the Megapack and Powerwall. These use LFP or sodium-ion chemistry. Energy density is low, 150 to 175 watt-hours per kilogram, but cost is the primary driver. By 2027, Tesla will likely transition the Megapack entirely to sodium-ion, achieving costs below $50 per kilowatt-hour. This makes grid storage economically competitive with natural gas peaker plants. So here's the map. Premium performance, high-nickel NCA. Mass market long range, 4680 mid-nickel. Mass market standard range, LFP. Robotaxi, single crystal NMC. Stationary storage, sodium ion. 5 chemistries, 5 markets. And notice what's missing. Aluminum ion, solid state, lithium sulfur. Those technologies are still in the lab. They're not production ready, and Tesla isn't waiting for them.
Instead, Tesla is optimizing the hell out of lithium-ion, diversifying into sodium-ion for cost-sensitive applications, and building the recycling infrastructure to make the whole system circular. That's the strategy. Last question, and this one's important. Which of these 5 segments do you think will have the biggest impact on the industry by 2027? Type premium, long range, standard, robotaxi, or storage? I have my own prediction, but I want to see where the audience thinks the margin expansion is actually going to come from. So let's come back to the original question. How close is Tesla to ending lithium batteries? The answer is, they're not ending lithium, they're perfecting it. Through Jeff Dan's longevity research, Tesla has solved the million-mile problem. Through Redwood Materials, they've built a closed-loop recycling system that makes virgin mining increasingly obsolete. Through the Corpus Christi refinery, they've achieved regional supply chain independence. And through the strategic deployment of LFP and sodium-ion, they've eliminated the expensive, conflict-prone materials like cobalt and high-grade nickel from the majority of their product line. Lithium isn't dying, it's evolving. The real shift happening in 2026 isn't chemical, it's structural. Tesla is moving from a world where batteries are consumable commodities, mined, used, and discarded, to a world where batteries are durable capital assets, recycled indefinitely, and optimized for specific use cases. If you're a supply chain manager, the takeaway is this: secure your LFP and sodium-ion partnerships now, because by 2027, the spot market will be too volatile. If you're an investor, the takeaway is this: the margin expansion story isn't in new chemistries, it's in manufacturing yield improvements on the 4680 dry electrode line and vertical integration through refining and recycling. And if you're an engineer, the takeaway is this: the next decade of battery innovation won't be about lab breakthroughs, it'll be about production engineering, thermal management, and life cycle optimization.
The companies that win will be the ones that can manufacture millions of cells per week with 99.9% yield rates, not the ones with the flashiest PowerPoint presentations about solid-state prototypes. So that's the roadmap, that's the reality, and that's what you need to be prepared for in 2026. If this breakdown gave you the clarity you were looking for, if you now understand the difference between production timelines and vaporware, subscribe to this channel, because every 2 weeks I'm releasing deep dive technical analysis that cuts through the hype and shows you what's actually being built. And here's the final ask. Drop the word recycle in the comments if you think closed-loop battery systems are the real revolution, or type sodium if you think sodium-ion is going to disrupt the market faster than most people expect. I read every single comment, and your answers directly shape the topics I cover next. Because in this industry, the future belongs to the manufacturers, not the dreamers. And if you're serious about understanding where this is going, you're in the right place.